Back everybody. This is our second session in JEE Mains previous year questions for chapter Wave Optics of class 12th. Before this video we have made one video in this series and that video is available on our YouTube channel's playlist section. We have also started a similar series for NEET previous years, so if some of your friends are preparing for NEET or if you want some additional practice, then you can watch those videos also. If you find these videos useful, helpful, then do press the like button, share them and subscribe to our channel. Also, if you like to support us financially, then you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Any amount of help will be highly appreciated. With this, let's start today's video. In the previous one, we covered up to question number 7 or 8 something. And today we will go next. This was the last question which we covered. Now, going to the question number 8. Two monochromatic light beam of intensity 16 and 9 units are interfering. The ratio of intensity of bright and dark fringe to the parts of the resultant pattern is. So, here we have to basically find out ratio of maxima to minima intensity. So, we know I max by I minimum is equal to under root I1 plus under root of I2 divided by under root of I1 minus under root I2 square. Now we have 16 and units 9 units as intensity, so we can say I1 is 16 and I2 is 9. So from this we will get 4 plus 3 divided by 4 minus 3 whole square, and that will be 49:1. That is option D. Now moving to the next one. And identical waves of intensity I node interfere with each other. The ratio of maximum intensity is the interference. Each is coherent and second one is incoherent. So we know that suppose we have two waves of intensity, amplitude A each. So we have two waves of amplitude A each. Now we know that this I node that will be proportional to square of the amplitude. So when these two waves add, what we get if they add coherently, so here we have coherent, then we will get 2A, and if they add incoherently, what we get? We get 0. Now in case of coherent addition, intensity will be 4A square, and here we will get intensity as 0. So basically if we add A plus A, we get 2A, and from that intensity is 4A square. Now let us take three waves, and if we add them coherently, so what we will get? We will get amplitude as 3A and intensity as 9A square. And if we add these waves incoherently, so amplitude will be either plus A or minus A, depending upon whether two are positive or two of them are of negative amplitude, and from that intensity will be basically just A square. So here if we are adding n waves here as n identical waves, so if we are adding n waves and assuming case 1 that n is even number, then for coherent addition, resultant amplitude will be n times A and resultant intensity will be n square times A square, and that will be basically n square times I node, because here I node is proportional to A square. So now for incoherent addition, as we have n is even, so our resultant will be 0 and resultant intensity for incoherent addition will be 0. So we will not going to have any their ratio, because we have to find out ratio of maximum intensity for coherent to incoherent. So that For this case, it will not be possible for n is equal to even. Now, if we take n is equal to odd, then what will happen? If n is odd, then coherent addition will stay the same. In coherent addition, again, resultant amplitude will be NA node and resultant intensity will be n squared times I node. Now, for incoherent addition, resultant amplitude can be plus minus A, and from that resultant intensity for incoherent addition will be just I node because it is proportional to A squared. So we can say their ratio will be n square I node by I node, that will be n square, and that is option A for us. So moving to the next one, a ray of light of intensity I is incident on a parallel glass slab at a point A as shown in the diagram. It undergoes partial reflection and refraction. At each reflection, 25% of the incident light is reflected. The ray A, B and A dash B dash undergoes an interference, the ratio of I max to I minimum. So here it is mentioned that it undergoes partial reflection and refraction, and each reflection we have 25% of the incident energy reflected. So we can say if this we have I node as incident, then B will be equal to 25 by 100 of I node, and here this transmitted wave will be 75 by 100 of I node. Now again at point C we have reflection, so we can say here we will get 75 by 100 by I node. This is the incident, and reflected wave will be 25% of that. So this will be 25 further. Now at point A dash again we are having transmission and reflection. This is the reflected wave and this is the transmitted wave. So A dash B dash is the transmitted, and for transmission we have 75% efficiency. So we can say that A dash B dash will be equal to 75. So 75 by 100 of I node. Oh sorry, there will be no I node because I node is here. Multiply the A dash C reflection factor, that is 25 by 100, and multiply the transmission factor for A dash B dash, that is 75 by 100. So this will be 1 by 4, this will be 3 by 4, and this will be again 3 by 4. So we will get 9 by 64 of I node, that is A dash B dash, and AB is just I node by 4. Now we have to find out maximum to minimum intensity ratio. So that can be calculated using, we know that I max by I minimum will be equal to under root I1 plus I2 under root I1 minus under root I2 square. So assuming this to be I1, okay, let us take this as I1. This is I1 because it has a larger amplitude, and it as a I2. So we will get under root I node by 2 plus 3 by 8 under root I node divided by under root I node by 2 minus 3 by 8 under root I node and whole square. And this will give us 1 by 2 plus 3 by 8, that will be 7 by 8 divided by half minus 3 by 8, that will be 1 by 8 and square. So that is 49 by 1. That is option A for us. Now let us move to the next one. Two coherent plane light waves of equal amplitude make small angle alpha with each other. They fall almost normally on a screen. If Lambda is the wavelength of the light. The fringe width delta x of the interference pattern of the two sets of the wave on the screen is. Now we know that fringe width is given by this general equation, that lambda capital D by small d. Here we have two coherent light sources, so assume that this is our screen and this is our first wave and this is our second wave, and they are making angle alpha with each other. So here this value of this small d is not given to us, and also value of capital D is also not given. But uh, if we let me draw a diagram here. Suppose this is our screen and this is our slit width here, this slit width, and we have to find out the beta here. So we know that suppose this is our central line which makes two slits here. Now for the fringe width, this is our central maxima and this is suppose our first maxima. So this angle theta, this distance y is our fringe width, or basically this is our beta. Now this beta can be written as, we know that theta is going to be r, that is beta, divided by the radius, and that distance is going to be d. So we can say from this that beta is theta times d. Now beta is lambda d by small d is equal to theta times d. Now d get cancelled, and from this we will get, so from this we can write that lambda is equal to d times theta. And if we come back here again and if we reverse this setup, now what we can draw here, we can make it look like this, that this is our screen, we reverse the direction of the light. So now light is making angle like this. Now this is the angle alpha. Now this spacing will act as small d and this spacing will act as capital D. Now from this we can write that small d by capital D is equal to alpha, and we can use this one in the expression for beta, that here we have beta is equal to lambda capital D by small d, and this can be written as lambda small d by capital D. Now small d by capital D from here is equal to alpha. So it becomes basically lambda by alpha, and it will match with option B. So option B is the right answer. Moving to the next one. The question has a paragraph followed by the two statements, statement 1 and statement 2. One of the given four alternatives for the statement, choose one which describes the statement. A thin air film formed by putting convex surface of a plane convex lens over the plane glass plate with monochromatic light. This film gives interference pattern due to light reflected from the top convex surface and the bottom glass plate of the surface of the statement 1. When light reflected from the glass air plate interference, reflected wave suffers phase change of phi. And statement 2. The center of the interference pattern is dark. So we know that when light is traveling from rare medium to denser medium and it suffers a reflection at the interface from rare to denser and it suffers a reflection, we have a phi phase change. And it is happening here that when light is traveling from air to glass, so air is rare medium, glass is a denser medium, so what will happen on the reflection, there will be phase change of phi, means statement 1 will be correct. And now as uh, the second light there will be no phase change. Means let me draw it. Suppose here we have convex surface. So suppose this is the plane mirror and this is our convex surface. So what happens here, that suppose this is the incident light. Now upon incident at this point, what happens, this light gets a phase change of pi, so means it becomes plus pi, and transmitted light goes without any phase change. Now upon striking here this is glass and this is also glass, so there will be no phase change, and so light keep on traveling like this. So when these two lights will meet or when they interfere with each other, what will happen, that this light has an additional phase of pi, due to which the condition for maxima and minima will interchange. And normally what we have, normally we have maxima at the center when there is no phase change, but now as there is a phase change of pi, so what we will get, we will get minima at the center. So that's why statement 2 is also right. So we can say both statement are right here, and here statement 1 will be the correct explanation for the statement 2. Note the statement 2 for the correct explanation of the statement 1. So if we see that both statements are true, and here statement 2 does not explain statement 1, actually statement 1 explains statement 2. So we can say here statement 2 is not correct explanation of statement 1. So option B will be right here, because 1 explains 2, that why the central fringe will be darker, because there will be phase change of phi. So 1 is explanation of 2, not the other way around. So moving to the next one. A initially parallel cylindrical beam travels in a medium of refractive index mu naught plus mu 2 I, where mu naught and mu 2 are positive constant and I is the intensity of the light beam. The intensity of the beam is decreasing with increasing radius. As the beam enters the medium, it will. So we have to find out that whether it will converge or diverge near the axis or travel in a cylindrical beam. So suppose this is our cylindrical beam. Now, as mentioned here, that refractive index mu I means refractive index is varying with intensity. So it is mu naught plus mu 2 I. So basically we can say refractive index is going to proportional to intensity. And also here it is mentioned that intensity of the beam is decreasing with increasing radius. So intensity is inversely proportional to radius. So from these two we can write that refractive index is inversely proportional to R, or we can say as radius is going to increase, refractive index is going to reduce. So if I draw it on this cylinder, this is one face of the cylinder. Now at the center we will have refractive index as mu naught, and as we move outside, radius is increasing on all the sides, and if radius is increasing, mu is decreasing. So means outside material will act as a rare medium and central material will act as a denser medium. Now we know that in denser medium wave travels slowly and in rarer medium waves travel fast. So this wave front will become like this. It will become like this. The central part will be traveling slowly and the outer part will be traveling faster. So this beam is basically what is happening here. We have converging here, convergence here. So that is option B for us. Now let us move to the next one. And initially parallel, okay, the statement is same. The initial shape of the wavefront of the beam is Now, initially the wave was in the cylindrical form, and the phase, suppose this phase is entering inside the medium, so this phase will be in the planar wavefront, because only when there is no refractive index change and wave is normally a planar wave. So we can say option B, and that's the basics of Huygens principle, that whenever a planar wavefront strikes or incident on some medium, then uh, it gets, we can say, either reflected or refracted, and depending upon the angle of means material refractive index, its angle will change, but it will again stay the same as the planar uh, refract, we can say, wavefront. Here suppose this is the boundary condition, and suppose this is the incident wavefront. So what happens to the incident wavefront, that suppose this is the normal and this is the second normal. So this wavefront start bending like this. This bends like this. So this angle changes, but it will, initially it was again planar and again it is again planar if the medium is a continuous medium. If we have a medium like a lens, then the structure of the wavefront will change. It will either become converging or become diverging. So here initially it was a planar wavefront. Okay, so speed of the light in medium is, so we have to find out speed of the light in the medium, and we already discussed in the first part of this one that in the center part it will act as a denser medium, so speed of light will be slow, and in the outer parts it will act as a rarer medium, so speed of light will be greater. So here we can say directly proportional to the intensity, maximum at the axis, minimum at the axis, that is option A, that it will be minimum at the axis. Now to demonstrate the phenomenon of interference, we require two sources which emit radiation of, and the condition is they should emit radiation of same frequency, and second is constant phase difference. So yes, that is option D for us. In the next one, Young's double slit experiment is performed using monochromatic light of wavelength lambda. Intensity of the light at a point on the screen where the path difference is k units. The intensity of the light at a point where path difference is lambda by 6 is n k by 12, where n is the integer value of nv to find out. So we know that we have a relation that I is equal to 4 I node cos square of phi by 2. If we have two sources of equal intensity, then this is the resultant intensity at some angle phi, some phase difference of phi. Now initially we have path difference of lambda. So from that we know that phi can be, we can calculate phi using the 2 pi by lambda into the delta x, this relation. So phi for lambda will be equal to 2 pi by lambda into lambda, that is 2 pi, and this will give us, so I for lambda it will be equal to 4 I node into cos square of pi. Now cos pi is minus 1, so this will be basically plus 1, and I lambda is equal to k, so from this k is equal to 4 I node. Now we have to find out for the lambda by 6, so phi for lambda by 6 will be equal to 2 pi by lambda into lambda by 6, and this is basically pi by 3, and intensity for lambda by 6 will be equal to 4 I node, that is basically k, so let's write it as k into cos square of pi, phi lambda by 6, that is pi by 3 divided by 2, so pi by 6. Now this is cos 30, and cos 30 is root 3 by 2, and square of that will be equal to 3 by 4, and we have to convert it into nk by 12. So we multiply it by 3 and divide by 3. So this is 9k by 12. So n is equal to 9 here. Now for the next one, we have Young's double slit experiment. Light of 500 nanometer is used to produce an interference pattern when a distance between the slit is 0.05 meter. Angular width in degree for the fringe formed on a distance screen closed. So we know that the fringe width is beta is lambda d by small d. Now angular width will be beta by capital D, that is lambda by small d. So lambda is 500 nanometers, so 10 raised to power minus 9 and divided by 5 into 10 raised to power minus 2 millimeters, so 10 raised to power minus 3. And this will give us 10 raised to power minus 2 radian. Now we know that pi radian is 180 degree. So we need to convert it into degrees because answer is in degree. So from that 1 radian will be 180 by pi degree, and if we multiply it, so 10 raised to power minus 2 into 180 divided by pi, and this will produce 57.3 into 10 raised to power minus 2 degrees, and it can be written as 0.573 degree. That is closest to option B. So option B is right here. Now in the next one, interference fringes are observed on the screen by illuminating two thin slits 1 millimeter apart. Light is wavelength is given, distance between the screen slit is given. If the bright fringe is observed on the screen at a distance 1.27 mm from the central bright fringe, then the path difference between the waves which are reaching this point from the slit is close to. Now we know that path difference in case of a interference pattern in the Young's double slit experiment is equal to d sine theta. Now assuming theta to be very small here, so this is basically d theta, and theta can be written as here, suppose this is screen and this is the light traveling from the two slits. So if this is angle theta, then this is the displacement from the central fringe, and this is slit screen distance d. So theta will be y by d. So there will be dy by capital D. So if we substitute values, here d is 10 raised to power minus 3 and the distance is given to be 100 centimeter. So we can say capital D. So capital D will be 1 because it is 100 centimeter. And bright fringe observed on the screen at a distance of from the central bright fringe means y is 1.27 millimeter, so 1.27 into 10 raised to power minus 3. So this is the path difference basically, and it will be 1.27 into 10 raised to power minus 6 meter. Now as mentioned that this is a point of maxima. Now for maxima we know that path difference should be equal to n times lambda, and lambda is here 632.8 we can say nanometer. So from this we can calculate n. So n will be 1.27 into 10 raised to power minus 6 divided by lambda, that is 632.8 divided by, here we have 10 raised to power minus 9, and this will be 1270 by 6328.8, and this will be approximately equal to 2. Means we are discussing here regarding second maxima, and for second maxima the difference will be only path difference will be d sine theta, means that is 1.27 into 10 to the power minus 3 meter, and that is 1.27 micrometer. So option A will be the right answer, because for second maxima we will have d sine theta is equal to n lambda, and for second maxima n will be equal to 1. Now with this we end this video here. Hopefully you understood it well, and best of luck for the any problem you are. If you have any doubts, you can put them in comment section, and if you like these videos, then do press the like and share button, and also if you like to donate us something, scan these QR codes. With this, again, thanks for watching, and we will meet in next